Hello, this is section 7.7 from James Stewart's Calculus Early Transcendentals book, and we are studying techniques of integration, and we've already covered many of the major techniques of integration to calculate an integral exactly. These methods include direct methods, a simple U substitution, maybe a trig substitution, integration by parts, integration by partial fractions, and algebraic manipulation to get to integration using direct methods, and integration using a table of integrals. Well, sometimes we've got some functions that we just cannot integrate using any of those techniques of integration. You see here in some of these examples of some non-elementary functions, e to the negative x squared dx, there is no technique of integration that will allow you to calculate that integral. Sine of x squared, sine x over x, etc. So what do we do in those scenarios? Because we do know that if f of x is a continuous function on a closed bounded interval from a to b, then the integral from a to b of f of x dx does exist. Well, we go back to the Riemann sum, or we go back to approximation methods, or numerical methods as a frequent term that is used. So we can't calculate exactly, but we can get pretty darn close. So if you recall in chapter 5, we learned how to approximate integrals using rectangles, a finite number of rectangles, and we developed a Riemann sum. And then we formulated the definition of the definite integral by taking the limit as n goes to infinity, and n being the number of rectangles goes to infinity. And if that limit exists, then we can calculate and define it to be the area under the curve. So today, we're going to go over the trapezoid rule, which is another numerical method or another approximation method to calculate or approximate the area under the curve, which is exactly what a definite integral is. So instead of using your standard rectangle, we're going to use a trapezoid. And so if you look at this graph here on the side of an elementary function or regular function, we can use trapezoids to approximate our curve. And what we do is that we take the outputs from our x sub 0 and our x sub 1, and we call them the lengths of the base of our rectangle, and we connect the dots between those function outputs, and we form a trapezoid with the first one being b sub 1 and b sub 2, and our height, which is perpendicular dropped between the two bases, would be our delta x. So if you remember what the area of a trapezoid is, if we have, and that's going to be equal to 1/2 times the height times the sum of the two bases. Good. And if we see here, the height of b1 is going to be f of x sub 0, the height of b2 is going to be f of x sub 1, and b3 is going to be f of x sub 2, and b4 here is going to be f of x sub 3, and dot, dot, dot. And you can see that we've got f of x k minus 1 is going to be our f of x sub k. That's our arbitrary slice. And we proceed until, and so we've got a series of rectangles, or trapezoids, sorry. And we can shade that region. And so you can see that we can approximate the area under the curve by adding up the areas of all of those rectangles. So if we look at this first line down here, and we know that our delta x from our Riemann sums, our delta x is going to be b minus a divided by n, where n is the number of trapezoids that we're approximating our function with, and b being the endpoints and a being an endpoint as well. So you can see that our area is approximately equal to 1/2, and you'll see that each one is, they just factored out, or this is our trapezoid number 1, and this is trapezoid 1, this is trapezoid number 2, this is trapezoid number 3, and this is trapezoid number K, and ... and this is trapezoid number, or T sub K number N. Good. So so the whole is equal to the sum of its parts. You can see that we have multiplied by 1/2 and delta x for each of the trapezoids, right? Because our delta x is our height, and we have that 1/2 from our area formula, and so we just factor those out into the front of our sum, because we can using the distributive property, and 1/2 delta x would give us delta x over 2. And now we've got a sum of function outputs, and notice that for all function outputs except for the very first one, f of x sub 0, and the very last one, f of x sub n, we have 2 of them, right? So we only have one of f of x sub 0, and we only have one of f of x sub n. So we only have one of them in here, but the other ones we see we have 2 terms, right? So we see f of x sub 1 plus f of x sub 1, and that's going to give us 2 of f of x sub 1. So that gives rise to a general formula that we can apply to use the trapezoid rule, and that's what this is. The integral of f of x dx from a to b is approximately equal to our 1/2 of delta x times f of x sub 0 plus f of x sub plus 2 plus 2, so every single one is internal. And we have that delta x is equal to b minus a over n, and we have that x sub I is equal to a plus I times delta x. Okay? And what is this a times I times delta x? Let's recall that if we have an interval from a to b, we do want our a to be x sub 0, and then we would divide our interval into n equal parts, and our b is always going to be b sub n, and we're going to add delta x each time, right? Our delta x is going to be that length. So you can see if this is going to be x sub 1, you can over here say a is equal to x sub 0, and you can just add delta x each time, or x sub 0 equal to a. So x sub 1 is going to be a just from delta x, and x sub 2 is just going to be x sub 1 plus delta x, and so you can see that that's going to be a plus 2 times delta x, and you can just keep adding delta x each time, right? And you should end up with x sub n equal to a plus n delta x, and you will get that x sub n should equal b. And you know that you've calculated each of those outputs correctly if you end up with the value of b at the very end for your nth term. All right, so that's going to end up being the case for the progression and calculation. You will start, so in this example here, we know already, because we can use direct methods to calculate the integral from 0 to 1 of 4 over 1 plus x squared dx, and we can actually calculate that exactly to equal pi. But here is just an example of using the trapezoid rule and seeing that we can get pretty darn close to pi by using this approximation method. So in this first example, we are using n equal to 2. Our first step would be calculate delta x. So delta x is that b minus a over n, and we know that a here is going to be 0, and b here is going to be 1. So our b minus a over n is going to be 1 minus 0 over 2, or 1/2. The second step will be to calculate your x sub i's. So find your all x sub i's, and so we start with x sub 0, and our x sub 0 is going to be a, and we know that a is equal to 0. Our x sub 1 is going to be a plus delta x, so that's going to be 0 plus 1/2, which is 1/2. And x sub 2 is going to be a plus 2 times delta x, and that's going to be 0 plus 2 times 1/2, and that's going to give me 1. Our third step is going to be calculate your f of x sub i's. Find all f of x sub i's. So in this case, we're going to find f of x sub 0, and that's going to be f of 0. We're going to find f of x sub 1, and that's going to be f of 1/2. And we're going to find f of x sub 2, and that's going to be f of 1. Good? And we know that f sub 0, knowing that this is our f of x is 4 over 1 plus x squared, we would get 4 over 1 plus 0 squared, or 4. F of 1/2 would be 4 over 1 plus 1/2 squared, which is 1/4. That's 4 over 5/4, and that's going to be 16/5. And f of 1 is going to be 4 over 1 plus 1 squared, which is 4 over 2, which is 2. Good? And then we will just take all of these values and plug them in here. So we would have our delta x, we would have our f of x sub 0, we would have our f of x sub 1, and we would have our f of x sub 2. And you can see in this progression, we saw that delta x was 1/2, so we substituted the 1/2. We calculated f sub 0, and f sub 0 is that 4 over, and we would get 4 here, right? This would be our 4, and plus 2, 4 over 1/2 squared would give us 16/5. And 4 over, this is going to give us our plus 2, and we distribute and we calculate, and we end up with 3.1. And that's pretty darn close to 3.14159, which is close to pi. And that's only using 2 trapezoid. So in the next step, we would do the same thing in n equal to 4. Notice that we would find our delta x, and with n equal to 4 here, we would want to find x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. And notice here, the x sub 0 starts with our a, and just adding delta x, we get 1/4. Adding another 4th, we get 2/4. Adding another 4th, we get 3/4. And adding another 4th, we get 1, and 1 does equal b. We are calculating our f values, and then we just distribute, and notice this is even closer to pi, right? So that's just a way of calculating the estimate using the trapezoid rule. And you can try it for yourself to use n equal to 6. Another method called Simpson's rule estimates using interpolation and taking 3 points on your graph of f of x and finding a parabola and calculating the area under the curve of that parabola. And it works out that the formula for Simpson's rule is you can estimate your function from a to b of f of x dx, or your integral, as delta x over 3 times, and again, the outer values of f of x sub 0 and f of x sub n only appear once, but now the coefficients alternate between 4 times the function value plus 2 times the function value plus 4 times the function value. So 4, 2, 4, 2, and you alternate until you get to the very end of your approximation. And please note, because of the way that Simpson's rule was developed and the formula was established, it does require that you use an even number of partitions, so n must be even in order to use Simpson's rule. So again, the technique is the same. You want to find your delta x. Your delta x is still going to be b minus a over n, and your xi's are still going to be a plus I times delta x. So you would still find those, and you would still want to start with that as a first step. You would want to find your f of x, or you find your xi's, and you would want to find your f of xi's, right? And knowing that a x sub 0 does start with a, and your x sub n ends with b, and you keep adding delta x for each one. And then once you find your xi's, you can find your f of xi's, and you know your formula for f of xi is always your integrand expression. And so you see here we are using our approximation is delta x over 3 of f of x sub 0. We begin with the coefficient 4. Since we only have two partitions, we only have x sub 0, x sub 1, x sub 2. So we don't need that 2 on the inside, and knowing that this one is the last one, right? The last term has coefficient 1. And the first term does too. Good. And so we substitute the values that we calculated, and we can come up with an approximation. And notice that using Simpson's rule on this very same example, 3.13 is close to pi. So you can feel confident that this is a pretty good approximation method. And again, we do it for n equal to 4, so it's a bit of a process, but note that we do begin with singular f of x sub 0, and we alternate 4, 2, 4, and we end with f of x sub 4 when we have. And that should be our f of b, just to be clear. And this one should be f of a, right? And again, look at that, 3.141569, that's super close to pi. Good. All right. So of course, in calculus, we want to know how far off are we in estimating our estimating the area under our curve using these numerical methods. And just going over some basic definitions, your absolute error is the difference between your approximation and the actual calculation. So that's why we used an example where you can calculate the exact area under the curve. And so in this case, it would be, in the case for n equal to 2 with the trapezoid rule, we would have 3.1 was our calculation, and we would subtract the exact value. And our relative error is going to be our absolute error over the exact value, right? So relative error would be absolute error over the exact value, and that's going to give us a decimal, which could give us a percent, right? And so you see that just in using two trapezoids, we were only off by 1.32%, and of the exact value, using n equal to 4, we were less than 1% off, which is pretty darn good. And you can see also with the Simpson's rule seems to be even more accurate than the trapezoid rule. So consider that as an option. All right, I'm going to stop here because I want to keep these videos short, and I'm going to do a part 2 in calculating the errors that we can estimate using the trapezoid